Good evening friends and welcome. Last session we have seen some numericals with different variety of single span beams. Today we shall cover a special case of single span beam which is having one end fixed, another end simply supported. That is a propped cantilever beam which is subjected to uniformly distributed load. Okay, so let us start. So this is a propped cantilever beam subjected to uniformly distributed load W. Its span we shall consider small l and AB is the beam. Okay. So just like previous question or previous session, we will assume that this is first of all a simply supported beam and we will draw its BMD. Okay. So if you consider this as a simply supported beam, bending moment diagram will be something like this, wherein there is this ordinate which is maximum at the center. It is equal to WL square by 8. And if you consider the fixity of end A, there will be fixed moment, something like this. Okay, M. So this is when elastic conditions are there. Similar bending moment diagram will be there when collapse state has occurred. Okay. And we have to find what is collapse load. Okay. So we shall assume that we have a moment, plastic moment corresponding to collapse load, which is occurring at x2, because from the given loading diagram we cannot identify location of plastic hinge. So for simplicity we have assumed x2 as the location from end B where plastic hinge will be formed. Now we have a section at x2, so what will be moment mx? If the beam is simply supported, this reaction will be how much? Total load is W, span is L, so equivalent point load is W into L. Half of this will be reaction here, so WL by 2. Okay. Into this x2, we shall assume this as x1. So WL by 2 into x2. Now you might ask, this is anti-clockwise movement, why not negative? So we have considered right hand side of the section. As per my assumption, I treat anti-clockwise movement on right hand side of the section as positive. Okay, so this is anti-clockwise movement. Next is this W. So this will be minus, because on right hand side moment due to this W will be clockwise. So minus W2 into this distance is x2 square by 2. So minus Wx2 square by 2, and we need to introduce now plastic moment here. So minus mp into x2 upon L, which is equal to mp, net plastic moment. Okay, net plastic moment. Now we will differentiate this because we do not know what is x2. So when we will differentiate this with respect to x2 and equate it to 0, we will get what is x2. So I'll write here dy dx or dy dx2 of mx is equal to 0. So first term, its derivative will be wl by 2, x2 will get vanished, its power will become 0, then minus w into x2. Why? x2 square is there, its derivative will be 2 times x2. 2 is there now in the numerator after derivative, so 2 gets cancelled with this 2 in the denominator, so remaining is only w into x2. So minus w x2 minus only x2 is there, so this will become 1 after derivative, so minus mp upon L. Okay, minus mp upon L. So this is derivative of mx. Equate this to 0, call this equation number. So this is equation 1 and this will be 2. Now solve equations 1 and 2 simultaneously. Solve equations 1 and 2 simultaneously. So we will get x2 is equal to 0.414 times L. Another variable is W, that is collapse load, which is what we require. It will be equal to 11.656 MP upon L square. 11.656 MP upon L square. So this is an important derivation. Propped cantilever subjected to UDL throughout. In this, we can directly say that location of plastic hinge is at 0.414 times L from simply supported end. Okay, location of plastic hinge is 0.414 times L from simply supported end, and corresponding collapse load is 11.656 upon L square times MP. Okay, thank you. Welcome again, friends. Now we shall see a fixed beam which is subjected to multiple concentrated loads. I have taken deliberately odd numbers, 0.3 L, 0.25 L, 1.5 times W, and so on. So this is a fixed beam AB. On C we can see 1.5 times W is the load. On D, W is the load. Position of 1.5 W is at 0.25 times L from A, and that of W is 0.3 L from B. Okay. Now we do not know in this case where will be exactly location of plastic hinge, but one thing is sure, that plastic hinge will be either under C or under D, because on both there are point loads. It is not like UDL, it can be anywhere. No. In case of point loads, it is only under the point loads. Plastic hinge will be under the point loads. Only that we have two options. One is under C, another is under D. So what we will do is, we will consider first that plastic hinge is under C. Second time we shall consider it under D, and then we will carry out the analysis. So we will have to carry out analysis, plastic analysis, 2 times. Okay, so let us start. Draw the deformed shape of the beam. our plastic hinge. First we will assume below C. So it is somewhere here. Okay. Now since load is not symmetric here, rotations will not be same on both the ends. So theta 1 and theta 2. Okay. There will be some deformation here also. So we shall assume this as delta 1 and this as delta 2. And now we will bring delta 1 in terms of theta 1, delta 2 also in terms of theta 1, theta 2 also in terms of theta 1. So simple geometry. First we will consider this right angled triangle where this side is 0.25 L. So theta 1 is equal to delta 1 divided by 0.25 L. Okay. So delta 1 is 0.25 L into theta 1. Another relationship of delta 1 with theta 2. So theta 2 is equal to, see now this right angled triangle. How much is this side? Total L minus 0.25 L. So this is 0.75 L. So theta 2 is equal to delta 1 upon 0.75 L. So from this delta 1 is 0.75 L theta 2. Equate both now. So 0.75 L theta 2 is equal to 0.25 L theta 1. So L gets cancelled from both the ends. So theta 2 is equal to 0.25 is 1 by 4. So I will rewrite this as theta 1 by 4. 0.35 is 3 by 4. Bring it on right hand side, so it will be 4 by 3. Okay. So 4 gets cancelled. So 1 by 3 is 0.33 theta 1. So theta 2 is 0.33 theta 1. Now we will bring theta 2, delta 2 in terms of theta 1. What is that? We have to consider now this smaller right angled triangle. So this side is 0.3 L. So theta 2 is equal to delta 2 divided by 0.3 L. Okay. So delta 2 is equal to 0.3 L times theta 2. Another equation for delta 2. Do we have anything? No. So we will substitute theta 2 in terms of theta 1 as this value. So this is equal to 0.3 or 1 by 3 L theta 2. So instead of L theta 2, instead of theta 2 we have 0.33 theta 1. So how much is 0.33? Again 1 by 3 into theta 1. So delta 2 is equal to 1 upon 9 theta 1. Okay. How much is 1 upon 9? 0.1 times theta 1. Okay. Now external work done and internal work done. We again have to go to basics. So internal work done is equal to, where are hinges? One is here because this is fixed end. So here is MP. Another is here. This is theta 1 and MP. This is theta 2 and MP. Here is one last hinge and its corresponding MP. So internal work done is 2 MP theta 1 plus 2 MP theta 2. So theta 2 in terms of theta 1 is 0.33 theta 1. So 2 MP theta 1 plus 2 times MP into theta 2 is 0.33 theta 1. So how much is total? 2 into 0.33 is 0.66 plus 2. So 2.66 MP theta 1. This is our internal work done. Now external work done. External work done is 1.5 W into delta 1 plus there is another external load. Do not forget this. W into delta 2. Substitute the values, everything in terms of theta 1. Okay. So 1.5 W into what is delta 1? 0. Delta 1 in terms of theta 1 0.25 L theta 1 plus W into, I think we have forgotten here, L. So this is theta 1 into L. So 0.1 theta 1 L. Okay. So take the addition now. 1.5 into 0.25 plus 0.1. How much? So 1.5 into 0.25 plus 0.1. So this total is 0.475 WL theta 1. Okay. Now we shall continue with our next part of the problem. Now we are going to consider hinge below point D. So now we shall draw the deformed shape. Then we shall show plastic hinge locations, moments, and then we will again complete our usual process, internal work done and external work done. Okay, so this is, we shall again say theta 1, this is theta 2, this is our delta 1, this is delta 2. Okay, here is again theta 1, theta 2, this is MP here, here is another MP, third MP with of course plastic hinge, and here is remaining plastic movement. Now we will again form the relationship between delta 1, theta 1, delta 2, theta 1. Okay, so now this smaller triangle, right angle triangle, so we will get from this delta 1 is equal to, this is 0.25 L theta 1, delta 2, this is larger triangle, so this is 1 minus 0.3, so 0.7 L theta 1. Anything else? Now we want theta 2 in terms of theta 1, so our another delta 2 value is 0.3 L theta 2. We will equate these two, so 0.3 L theta 2 is equal to 0.7 L theta 1. So from this theta 2 is equal to, I'll get calci in a minute. So 0.7 upon 0.3 is 2.33 theta 1. Okay, so all these three values we have got. Theta 2 is equal. So now we will go for internal work done. Okay, internal work done is equal to, this is mp theta 1 2 times, and this is mp theta 2 2 times. So substitute the value of theta 2 here as 2.33 theta 1. So how much is total? 2 times 2.33 is 4.66 plus 2 is 6.66 mp theta 1. Okay, now external work done. What is external work done? 1.5 W into delta 1 plus W into delta 2. So 1.5 W, what is delta 1? In terms of theta 1, 0.25 L theta 1 plus W into delta 2 in terms of theta 1 is 0.7 L theta 1. Okay. So we will simplify external work done first. External work done is equal to 1.5 into 0.25 plus 0.7. So it is 1.075. 1.075 WL theta 1. Okay, now we will equate external work done to internal work done. So 1.075 WL theta 1 is equal to 6.66 MP theta 1. So W is equal to 6.66 upon 1.075 MP upon L. So see how much is this ratio. 6.66 upon 1.075. So it is 6.2. 6.2 MP upon L. So we have two answers of collapse load. One is with previous case, that is plastic hinge below C. With respect to this situation, we have collapse load 5.6 MP upon L. Second situation, plastic hinge below D. Here we have 6.2 MP upon L. So you consider list of these two values. Okay. So our answer is 6.2 times MP by L. Though we have two values. Now why this? Because it is not necessary that plastic hinge will form. Our answer is 5.6 MP by L, not this one. Because it is not necessary that plastic hinge will not form under C and it will form under D. No, it can form here also. So we have to take this possibility. We have to give priority to this case because at lower value of collapse load, beam may fail. It need not go more than this value. Here also it can fail. But now this has been asked, it is asked that you have to find collapse load. If you are asked to find plastic moment, then from this what will be plastic moment? MP is equal to C. Here collapse load is 5.6 MP upon L. So from this MP is how much? WL upon 5.6, and here MP is equal to WL upon 6.2. So which value will be more? Plastic moment, this value, okay, and this will be less. So when you are asked to find collapse load, go with lesser magnitude. When you are asked to find plastic moment, go with higher magnitude. Okay, in this case again this 1 upon 5.6 is higher magnitude, so plastic moment value will be higher of all the values and collapse load will be least of all the values calculated. Okay, thank you.